Hello everybody, my name is Kira Chen and this is a presentation on Hilbert's 10th problem, lemma 2.9 to 2.16. This is a paper from Martin Davis. I have the wonderful Luke Sperling to help me prepare this presentation. So to start things off, I'd like to present some important notations that we use throughout this presentation. So from the previous presentation from Gabe Appleton, we learned that this is an equation that is used throughout the entire paper. So whenever the author uses this equation, he often represents the first part, which is the rational portion of this equation, as x of n. So when you see x of n used in the paper, it is representing the coefficient of the rational portion of this equation. When you see y of m, it is representing the irrational portion of this function. So the last thing that we have to learn is x bar y represents that y is divisible by x. So when you see 2 bar 10, this means that 10 is divisible by 2. So to start things off, we have lemma 2.9. So what 2.9 is saying that is y of t is divisible by y of n if and only if t is divisible by n. So if we consider lemma 2.8, we prove that y of n times k is divisible by y of n. Intuitively, we can think of this as n times k is divisible by n because we multiply n by k. So if t is divisible by n, then t must be in the form of n times q, where q is just any factor that you multiply n by. So suppose we want a more concrete version of this proof. We're going to do this by a contradiction. So let's say that y of t is divisible by y of n, but t is not divisible by n. So this is the opposite of what our assumption is in the lemma. Then we can say that t has to be of nq plus r, where r is some remainder because since t is not divisible by n, we have n times q and then some remainder left. It is important to note that r has to be between n and 0 because if r is equals to n, then there's a factor that you can divide out of it. This implies that t is divisible by n. If r is greater than n, then we can also take a factor of n out of r. Now if we apply lemma 2.5 to y of nq plus r, where we have this function, we have two parts of this function. So the first part is xr, y, and q. This has this part in it, which is divisible by y and q. If we consider the other part, we can say that x of nq times y of r is divisible by y of n because this is the other portion of this equation. However, from lemma 2.8, we know that the GCD of y of n and x of nq has to be 1. So hence, y of r has to be divisible by y of n because of that. But this implies that r is greater than n, since r is divisible by n. And y of r is less than y of n. Well, this has to be a contradiction because if we think about it, 10 divided by 5 cannot simultaneously mean that 5 is greater than 10. One has to be greater than the other one to be divisible by it. So that contradiction is in essence why we have this lemma is true. So the lemma again is saying that y of t is divisible by y of n if and only if t is divisible by n. So to understand lemma 2.10, I first have to define the notion of what the author means when he uses the triple equal sign. Whenever you see this triple equal sign in this paper, it means that the left-hand side of this equal sign and the right-hand side of this equal sign is both have the same result when you mod it by this part here. So what this is saying is that the modulo of y times nk by y of n cubed is the same as k times xn k minus 1 times y of n mod y of n cubed. And here's the proof of it. So we consider the first equation of xnk plus ynk square root of d. We can rewrite this such as a plus d to the power of square root of d. Now we can expand this form to be a plus square root of d to the power of n to the power of k. Now applying our notion of xn and xy, now we have xn plus yn square root of d to the power of k. Now we consider the binomial coefficient where x plus y to the power of n, we can expand this in the form of the summation of k equals to 0 to n, kn, xn minus k, and y to the k. If we apply the equation that we have above here to the binomial coefficient, we have this function, summation of j0 to the power of k, k choose j, xn, k minus j, yn to the power of j. And now we have this term of dj divided by 2. So this term is rather interesting because it derives from this square root of d. So square root of d is the same thing as d to the power of 1/2. Now if we consider this, when you have d to the power of 1/2, d to the power of 3/2, and so on, these are irrationals, whereas d to the power of 2/2 is 1, d to the power of 4/2 is 2, so these are rational. When you have a fraction in this power, it is irrational, whereas if it's a whole number, we have a rational. Now, if we consider this form where we only consider j starting from 1, and if j is odd, and now we have j minus 1 here, we have this special property where if j is 1, then d is raised to the power of 0, so the d term completely disappears. Now, if j is greater than 1 and is odd, we do not have irrationals since this is now even. So if this is odd, so now we have, say, 5 minus 1. So if j is 5, we have 5 minus 1 divided by 2. Now, d to the power of 2 is rational. And since the author uses x of n to represent the rational, this term now belongs to x of n, and it essentially disappears. Now we can say that all the terms in where j is greater than 1 contains this y of n to the power of j, which can be multiplied by y of n 3. So lemma 2.11 is more nice properties of y's of n. So what this one is saying is y's of n to y's of n is divisible by y's of n squared. To prove this one, we simply plug this into lemma 2.10, where we set k is equals to y of n. So this is the equation that we have from lemma 2.10. If we plug in y of n where k is, we have this equation where there's now 2 y's of n. So y's of n squared is on this side, and y's of n, y's of n. Lemma 2.12 is saying that if y sub t is divisible by y sub n squared, then so is t divisible by y sub n. Now in 2.9 we show that if t is divisible by n, then y of t is also divisible by y of n. Now if we set t equals to nk here, and then we apply this to lemma 2.10, we get this equation. So y of n squared kxn to the power of k minus 1 and y of n. Now, if we divide both sides by y of n, so we take these out, we obtain this equation here. Now, as we know in 2.7, y's of n of x of n has a GCD of 1. So y's of n is greater than, or k is divisible by y's of n, and hence t is also divisible by y of n. So moving on to lemma 2.13, this one is actually really easy relative to the previous one. So what this one really is saying is that x of n plus 1 has this nice property that it is also equals to 2a times x of n minus x of n minus 1. And the same equation applies to y of n plus 1. So to derive this, we use lemma 2.6 where we have these two equations. So from lemma 2.6, we have xn plus 1 equals to axn plus dyn, and xn minus 1 equals to 2xn minus dyn. Now if we combine the two equations, now we have x of n plus 1 plus x of n minus 1 equals to 2ax minus 1. So we just simply add the two equations together on each side. These two terms cancel out. This is the same thing, so you have 2axn, and these two simply adds together. Now we just move this term over, and we derive this equation. If we do the same thing for y of n, we also derive the same equation. So looking at lemma 2.14, we have this property where y's of n and n is both multiple by a minus 1, and it has the same result. To prove this one, we use induction. So when n is 0 and 1, this equality holds. Now we just induct on, so y's of n plus 1, we use this lemma from 2.13. Remember, we got this function from 2.13. And we induct with n as well. And mod a minus 1, it should exactly be the same. So lemma 2.15 is relatively similar to 2.14 in the sense that they're both using induction to prove that left part and right part mod c is the same result. For 2.15, we have a, b mod c is the same. And we know we're going to show that for xn and yn, this equation also holds true. So for n equals to 0 and 1, we know this congruence is true. Now, using induction, we can prove that the rest of this lemma is true because So this is the equation that we derived from a couple lemmas ago. So remember, yn plus 1a is equals to 2a yn a minus yn plus 1a. And we do the same thing with yn plus 1b, and since this equation holds true for mod c, it's the same thing. And you can prove this inductively. And lastly, we have lemma 2.16. So 2.16 is pretty simple. It's saying that when n is even, y of n is also even. And when n is odd, y of n is odd. And this is pretty easy to prove because what the author did here is he did y of n plus 1 and y of n minus 1 mod 2 is true. So if we think about it, this is every other number is odd and every other number is even. So 0 is even, 2 is even, 4 is even, 1 is odd, 3 is odd, and so on. And he's simply saying that the same relationship applies to y of n plus 1 and y of n minus 1. That would be all for this presentation. Thank you all for tuning in, and again, thank you for Luke Sperling helping me with this presentation.